We're going to talk a little bit about a geometric distribution. Please don't get confused about this. This is just one other type of distribution. I do not have a lot of problems assigned about this, nor do I have many test questions about this, but I just want you to be aware of what it is. A geometric distribution has to meet three different characteristics, and one is that there are one or more of these Bernoulli trials, and that just means the odds of having a success are the same for each trial, and the failure then of course would be the same for each trial, and that there are only two options, very similar to the binomial distribution where it's either a success or a failure. So that's what the Bernoulli trials is, and it's all failures until you get to the last one, meaning that you're going to keep trying until you get it right. So that's what a geometric distribution needs to have as one of its characteristics. The other one is, in theory, the number of trials could go on forever, and there has to be at least one trial. So if you never got a success, you could keep going with the trial, is what that means in theory. The probability of success and the probability of a failure are the same for each trial. It's not going to change. It's not dependent on what happened last time. And X is the number of independent trials until the first success. So it does not count that last one, it just counts those failures until you get to the first success. So that is a geometric distribution. Here's kind of an example so you can understand it maybe a little further. You play a game of chance. You can either win or lose. No other possibilities, no ties. And until you lose, right? You lose until you lose. You play it until you lose. Your probability of losing is 0.57. What's the probability that it takes 5 games until you lose? That's where we're talking our X can take on 1 game, 2 games, 3 games, 4 games, and 5 games. So the question is, what is the probability that X equals 5? The notation for this, very similar to the binomial distribution. We have the G in there and the P, meaning the probability of success for each trial. Here's another example. A defective computer component, that probability is 0.02. Components are selected at random. What's the probability that the first defect is caused by the 7th component tested? So you would test 6 and that 7th one would have that defect in it. So X is the number of computer components tested until the first defect is found. So X can take on the values 1, 2, 3, and so forth. And we have our probability. And the notation then is this. Why is that notation important? Well, because when we go to solve this, if we put it into our calculator, we want to make sure we understand that notation. We again would go to the right here for our calculator, hit the second button and the distribution button, and scroll down till we find the geometric probability distribution. Enter that, and then enter the notation just like we had it, and push enter to see the results of X equaling 7. So the probability, if you wanted to find the probability of everything under 7 and up to 7, at least 7, so it could be 0, it could be 1, it could be 2, and it could be all the way up until, at most is what I meant, it could be all the way up to 7. Follow the same instructions except change the formula and have it with that symbol. The probability of that 7th component is the first defect is then there. Okay. Hopefully that makes sense. Like I say, this is geometric distribution. We're not using a lot of it, but I just wanted you to know what it is. And here's the formulas that go with it. They're in the book as well. Our mu is 1 over the probability. Our variance is our mu times that complement, and our standard deviation is the square root of that. So the more specific that our distributions get, the simpler their formulas get. We start with a wider formula that is a little more difficult to understand. That includes all different probability distributions. Binomial probability distribution has a little simpler formulas because it meets different criteria. And then the geometric meets a couple of more criteria, and those are even simpler. So that's just one way to look at it. This problem here, again, it tells us how to go about setting this up. By setting it up, we really mean how can we enter this into our calculator? And I'm going to put my face up there. Here's the solution to that. So if you want to go back and forth between it, we have what we are going to enter into our geometric probability distribution and the results that we get. And we find the mu by doing 1 over the probability and our standard deviation there. Hopefully you won't find any trouble with these. They're pretty straightforward formula, works, and you don't have to really understand how to put too much effort into it. The calculator does a lot of the work in this case. Good luck.